Good day to you. This is Galactic. On the 18th day of June, this evening, you should be able to see a crescent moon. It should be the first night that it's visible. Now, up here in the upper corner, you'll see me in a previous incarnation. This is a video I made not too long ago. I have been covering the number system for a new geometry, which is basically very simple. It's just curvature geometry. The straight line is simply a simplistic derivative version of a much more robust number system called proportional number space. It does form a space. We now wish to turn to this video that I made not too long ago because it explains perfectly what I want to say about the geometry of space. This will dovetail perfectly with our discussion of numbers, which going too far in that direction divorces you from reality. Mathematics is a tool for geometry, but it is necessary to have the mathematical basis for a geometry. That's why we say linear, linear, linear. Everything is linear. The non-Euclidean geometry, supposedly discovered by Bolyai and Lobachevsky, is not non-Euclidean. That's simply a violation of the parallel postulate. It was used by Albert Einstein to compose space-time, forced by Euclidean geometry. General relativity is considered to be a construction of gravity. What Albert Einstein was attempting to do was to get an integral solution for gravity in a multi-body system, including all the energy in the system. That requires an integration so that he could formulate gravity on the basis of the content of the space. That is fairly well established. It certainly works, but it uses linear mathematics, and that's why a human being can neither perform the operation nor understand it. Albert Einstein invented supercalculus or hypercalculus, four-dimensional calculus. He managed to do it. It's a linear solution to a spherical equation. This is spherical geometry reduced to the quantum level. Thank you for tuning in to Galactic. Here we go. This is Galactic, coming right back at you with the secrets of the universe. We're now going to delve into quantum mechanics in order to get at cosmology. This has never been attempted, but it is dreamt of. The way to begin is to realize what the quantum is. It was discovered by Max Planck, although he didn't really like his discovery, because it introduced a step function into what had until then been considered to be necessarily a continuous function. Also the view of Newton, although he dealt with the problem of continuity, both in space and in time, mostly with a wave of his hand because he had no way to extrapolate, but he obviously wanted to, he simply could not. His corpuscular theory of light is necessarily quantum, because corpuscles would be quanta. That is, in fact, what Einstein said as well in his proof of the photoelectric effect, which directly implies that energy is quantized. This was a validation of Planck's earlier discoveries. This is a major discovery that energy is quantized, as indeed seems to be the case according to how this was figured out. Well, how was it figured out? The best way to look at the quantum is to realize why it was so significantly different than what was expected, first of all by Planck, and next of all by anyone else who knew what Planck had found. Nobody liked it. But it finally came to be accepted largely due to Einstein, who showed that the photon really is the quantum. That turns out to be only one part of a superpositional story. It is a wrench to traditional logic because it implies a two-part logical entity, which normally would be just a one part. It's either yes or no. But in the case of superposition, you could actually have yes and no superimposed. This is, in fact, Schrödinger's cat paradox. Alive and dead is the same thing as yes and no. He chose the cat being murdered in order to show the absurdity. Schrödinger was in the same position as Planck, exposing what the mathematics shows, what he found, which he did not like, for the same reason that Planck did not like his own discovery. The fact that they were both ultimately considered to be correct really has two aspects. There is still a quantum paradox. The first way to get at the quantum paradox, to make it not a paradox, is to realize what is the quantum. There are several definitions of the quantum, but I want to cut this short. There's always a trade-off when you cut things short. So the quantum can be extraordinarily simplified conceptually by just adding one word. It's a linear quantum. This is forced by the mathematics we have been using basically for 2,000 years, which is linear mathematics. The only way to get it, what ended up being the quantum, was with linear algebra. What Planck apparently proved is that in an energy transfer, it's not continuous. That actually doesn't make sense, and that's really why it's a paradox and why it was not liked. What I'd like to do now is gently introduce us into the nature of the quantum according to the first man who had a direct perception of this problem. At a level which is actually philosophical, but it's scientific philosophy. The man's name is Rudger Bošković, as you know. His discovery, which he made around 1745, what he was coming to grips with is what essentially Newton and Leibniz had just discovered, which was access to curvature, access to curve space. It was a major breakthrough in the history of mathematics because obviously linear algebra with our linear number system is not innately equipped to address curvature. The calculus was a major tool. Curvature has always been considered to be a major goal, so no one really had too much of an idea of sphericity, except in terms of, for instance, spherical trigonometry to compute distances and relationships on the surface of the Earth, which is a sphere, but nobody ever had to face the sphere as such until the 20th century. And it's remarkable to me, just as a coincidence, that Max Planck made his discovery of the quantum in the year 1900. And that really is the turning point. Because what he was talking about essentially is a spherical function. The spherical number system is very easy to conceive. The natural question arises, how come nobody else has discovered this? The line is based on the operator add, but the sphere is based on the operator multiply. The operator for the line and the operator for the sphere. In the case of the line, it's easy to say add subsumes subtraction. And you're subtracting a negative number, that's the same thing as adding a positive number. So what about multiplication? Well, multiplication and division are equally simple, but it does not appear so when you're attempting to use them on the line, which we always have. The problem was not recognized except as an innate problem of linear algebra, which is correct. It is that if you attempt to use multiplication with its inverse, we didn't know that this was a spherical operation. It's remarkable to say that you can come at this by approaching it from the point of view of the two identity numbers, because addition and subtraction have one identity number 0. But when you have the multiplicative identity, the 1, the Archimedean, on the line it would be a point. So the Archimedean balance point of the line is 0. But the Archimedean balance something of the something is 1. And that's not going to be the line. It's easy, once you know how, to get a spherical number system for all of space. So in terms of having to come to grips with a sphere, all we needed was spherical trigonometry, which is a nightmare to learn. For obvious reasons, you're using a cubic grid to compute a spherical surface, such as the Earth. Airline distances on the Earth can be computed with polar coordinate algebra. You are using lines to compute curvature, which literally can't be done unless you tweak the numbers. And the way you can do that is either by composing a higher order number system, that's what the complex number system is, utilizing the square root of -1 as the scale for the second basis axis, induces a circular function which then can be realized on the natural logarithm. So that's in a nutshell. Those are not linear numbers. And so you need a special algebra in order to translate back into linear numbers, which you always need to do because those are the computable numbers. When I was programming spherical trigonometry, computing rotations, approximately 5 methods, none of them adequate. Instead of using complexity, which is imaginarity, to get a circular function, Einstein did the same thing for cubic space by adding a fourth imaginary axis to get complexity, which complexity is a stupid term, but we're stuck with it. All it means is rotational. That is circularity. But in volume space, that is cubic space, it's no longer a circular function, it's a spherical function. And he used that to compute gravity. He needed the spherical functionality because, first of all, gravitational space is spherical. Well, that was brand new. Nobody had ever computed anything like that before. When computing spherical volume, that's been known since ancient times. Here we're referring to the surface. It's called a surface because you're not talking about the inside or outside. You're talking about the geometry, in this case of the space, both for the atom and for the universe. We're not trying to compute distances on a sphere, but that's not what we're trying to do in physics. What's happened is in the 20th century, in the two spherical directions, that is going out towards the edge of the universe and going in towards the center of the atom, these would be two opposite spherical directions, although they're not directly correlated, they're obviously opposite directions. Well, those are two opposite directions in physics. And they're final, they're ultimate, it's binary. If it's a spherical direction, this would be a force, by the way. You're either going in, which is gravity, or you're going out, which is light. Okay? So those are the two balanced forces of the universe, and this is a direct lead into the Boškovićian force curve system. It's a mechanical system. Remember, Bošković lived in the 18th century. He was a small lad when both Leibniz and Newton kicked the bucket, and then Bošković rose to the top, and he became the next greatest of the physicists and mathematicians. It is more difficult to say mathematician. Definitely the most respected physicist in Europe, and at that time England was not really exactly the same thing as Europe, as Leibniz and Newton sure proved, but he actually visited England. And he was very well received there. I believe he was made a fellow, which the English were quite generous in that sense. If they recognized a scientist, even if he was from the continent, they liked that. Although they'd continue to argue if they had to, which occurred between the followers of Newton and Leibniz and only recently has subsided at all. So these paradoxes go on for a long time. In the case of the calculus, it was over the nature of the infinitesimal, essentially. Well, actually what it was precedence and who discovered it, because it was of national importance, to the pride of the nation. But the difference they did have a different approach to calculus, and actually a different definition of what the calculus was. What we know now is that both definitions are required. And what is the difference? This leads directly into our subject, so don't think I'm trying to deviate. But this is a multi-pronged approach to the most difficult problem of all time in physics, is the unification of essentially microphysics with macrophysics. What does that imply? It means the unification of quantum mechanics is what it would be now, or electrodynamics, both of which occur at the atomic level, or really the subatomic level, the intra-atomic level. What is the atom is more than one thing. It's really two things, right? So that's the atom. But if you go to the edge of the universe, which would be pretty much in the opposite direction, then you have an integral problem. Now, the integral problem, which is unbounded space, what do you do with that? We have to call it infinity, which is not a number, and that's a major problem. So the calculus tends to solve that, but it's not really the integral that is the problem. It's the infinitesimal. What I discovered is those are reciprocal in spherical space, which is a remarkable discovery, and let's make sure we understand that right now because it's not difficult. In fact, one of the really strange things about this geometry is it's so remarkably straightforwardly simple. But it does require a certain leap at a certain point. All right, so as I said, but it's worth saying again because this is a major discovery, I claim. If you attempt to compose spherical space, first of all, you have to realize, which has been proved, that you can't abandon the linear numbers. So you're going to have to prove first, or at some point, pardon me, keep using the word point, you have to show that the linear numbers are extractable. as indeed conjugate algebra is required in order to get linear numbers back from complex numbers, because complex numbers are not computable. But the algebra makes it consistent, and you first switch systems to the complex system. This is also done in spacetime by switching from 3D cubic space to 4D spacetime. Exactly the same thing, except instead of the circular function you're getting with complex numbers, in spacetime you're getting the spherical function. Which in the case of Einstein, just to jump ahead because this is important, he needed to deal with simultaneity in volume space. This is why he was including time. It's really the time differential, which is, you can see differential has to do with an infinitesimal, but actually his problem was integral. He was trying to integrate a volume space to compute gravity for that space, to show its geometry. Because as you know, it's based on a center and a sphere. That's called the center of gravity for the solar system, or the Earth, or in fact any macroscale body larger than a satellite such as the size of the moon. Because it does have to be spherical, although even asteroids have gravity, and we've proved that by landing on them and sticking. That can be computed, but it's very... even though it's an elongated object, it will still... this is difficult to say, but it will have a center of gravity. That is true. In linear algebra, that has to be a point. That is a zero, which is saying the same thing for the center. Now, in spherical space, it's a bit different. And here's how we know that. It's for, in other words, what the problem that we're having, both in quantum mechanics and in cosmology, is the nature of the center of the space, which is not linear. What I discovered is the numeric value of the center of any spherical geometry has a specific number. It's remarkable because it's an imaginary number, and it would have to be, and that matches what Rudger Bošković discovered, which is the impenetrability of a particle. Now, I've discovered that there's only one particle, and that's rigorously provable. So even though it goes against subatomic particle physicists, you should know something about what subatomic particle physicists are attempting to classify in the Standard Model. Those are not particles, they can't be, but they have to call them particles because there's no other word. But the real definition of a particle is something that forms a center in space, and there's only one of those, a proton. So the unique characteristic or property is a better word of a proton is that it bends space, and Albert Einstein proved that, but he didn't prove it for the proton, he proved it for gravity. But I can tell you, and you can learn from me, that the correct definition, a mechanical definition, would be a proper way to characterize this definition of gravity. It's that it's integral protonic centripetal force. That is a fact, and it's actually tautological, but it leads to certain conflicts with other theoretical models. But this is the right one, and you can accept that from me because I'm right, and I've proved it, so it's true. So that is the nature of the particle, is that it bends space. That's a proton. And the proton, therefore, is the only particle using this approach. But what that means is that you have to be sure of what you mean by the center. And the proton, is it a center, or does it have a center, or both, or neither? How can you relate the concept of a spherical center to a proton? You do it using Rudger Bošković's force curve mechanics, and that's being realized now by top-level physicists who are hesitant to say so, and those who have said so are getting marginalized. Because it goes against what the government wants, and I'm not going to go into that because that would lead to a rant or something distracting. But you do need to know why this is not being pursued, even though it's being known, I'll put it that way in the progressive sense, that the quantum mechanical paradox is based on a misperception of what is the center of anything, which in this case would be a proton. But actually, the quantum mechanical paradox comes up in context of the electron. Now, therefore, it's going to become necessary to distinguish between the proton and the electron as particles. They're both considered to be particles, and I do consider them both to be particles, but it's superpositional, and it has to be superpositional. And superpositional means that you have two conflicting definitions that are both true, but they can't be true at the same time. Very strange, but that is the nature of superposition. Electromagnetism is a good example of how you need to start thinking differently about what a phenomenon is at this level, because magnetism obviously is a manifestation of centripetal force. If you put two magnets near enough each other and oriented correctly, they'll move toward each other and crash into each other because of centripetal force. It's a mutual centripetal force, just as if they were gravitational bodies. Well, obviously that shows the relationship between magnetism, which is a component of electromagnetism, obviously, and gravity. The problem with that, then, is there is no electro component to go with gravity. So nobody knows where the electro component went. So all of this is part of the broad picture that physics is facing, which it really has stymied everybody. I'm going to show you the way through this so that it all makes sense. But obviously, nobody has been able to see this thus far, so bear with me as I attempt to make this simple. If you look at the atom and consider its geometry, it's obviously spherical, and nobody argues that. The reason it's spherical, and this can be stated even without a proof, although it can be proved, is that the reason that the atom is shaped as a sphere, that is with electronic shells, shells made of electrons. Those are quantum shells, by the way, and this is well known. The electrons will only go to certain radial distances from a protonic core, which differs according to the number of protons. But we've analyzed the simplex hydrogen atom, which is simply one proton and one electron, and extending that to the next atom in the periodic table, which would be two protons and two electrons. We're ignoring the neutrons now. That also makes the case interesting. But when it's just one proton and one electron, anywhere in the universe is going to be the same fixed radius from the proton. But is it from the proton or from the center of the proton? You might say that it makes no difference which one you say, since they're concentric shells. And so, but it would be a different distance, wouldn't it? So the question is, does the proton have a radius? And the answer is yes, it does. But then that raises an issue. Is the proton solid? That is, could it be penetrated? And if you would, this is the reason for the cyclotrons, and they're now called hadron colliders, is to essentially crash two protons together to see what comes out, because there's a great incentive to find out what's inside the proton, because it's a potential source of power. In fact, it's surmised, and I would say most likely rightly so, that it would surpass fusion power. This is called the strong force, although that's ambiguous, but you can just think of it as the force that controls the proton's cohesion. Now, the proton does have a known structure, but it's a mathematical structure called the 3-quark harmonic, and that's the right way to say it, and only I will say it that way, but any physicist who is cornered would say it and then regret that they agreed with me, but that is correct. So the quarks are not particles, and that has been proved. And it's been admitted, too, that although they're called particles, even the subatomic particle physicists have to face it. They don't advertise this because it's contrary to policy. Because just to say that the quarks are particles makes the public excited, and so they're more apt to go along with the military. It's the military who's driving subatomic particle physics, of course. It's not entirely true, but it's true enough since it's 99% of the money. So, the proton, is it a particle or not? It comes down to what you mean by a particle, and it's also superpositional. And it has to do with the most basic geometry in the universe. So let's take a look in our minds. Just picture a circle. We cannot picture a sphere in our minds. But if you think you can, go ahead. I think I can too. But it doesn't make any difference. And of course it does. It's superpositional. But let's just say it's a sphere. Picture a sphere in your mind. All right. That obviously has a center, correct? All right. How small can that sphere be before it stops being a sphere? It sounds like a riddle, doesn't it? In other words, where does the sphere contract to? Well, in linear algebra, it contracts to 0, right? Which then is not a sphere. So that's a direct contradiction. So spherical geometry entails a different number basis because 0 does not exist. If you could, or you could say, if the center is 0 in spherical space, then it's virtual. And there can be no particle of that size. That would sound more rational, I think. But then you're stuck with another paradox, which is, how small can a particle be before it can't be a particle? This would apply to the proton, and the answer is, I would say, disconcerting, because it doesn't match anything in known mechanics, and it really couldn't. So this is a predictable paradox, but it remains a paradox, predictable or not. How small is the proton? And that is extraordinarily difficult to say. But we do know its inner range, and you can find diagrams of this in Wikipedia showing the nuclear force, which is an ambiguous term, but in the context that we're speaking of nuclear force, the simplest form of visualization of nuclear force is one proton exerting a force which is considered to be a field. And that is a mathematical term, although remember it's a linear mathematical term. But a field is the area, you should say space, around the proton. Now, we know something about that force. We call it plus charge, but I'd like you to just put a question mark with plus charge and minus charge. Because the only way we know about plus charge and minus charge is that the electron is minus and the proton is plus. And those are identities. What we call negative charge refers to the electron, and what we call positive charge refers to the proton. But that positive charge is precisely gravity. There's no difference between that and gravity. Both are centripetal forces. The only way we can measure plus charge, unless it's in terms of electrical engineering where the meaning changes, because then you're talking about integral electronic force and integral, well, these would be plus and minus charge in an electrical system. You can think of this atom, just one proton and one electron, as being the world's smallest electrical system, with a minus charge, and this is how it's shown in diagrams, with a minus charge orbiting in spherically, not on a disk as it is in macrospace, but in, that's why you see these 3 circles drawn around a center with little dots in it, which is supposed to be the symbol for nuclear energy. Circle, 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 all making basically a hexagon. And then a protonic core. That's a small electrical system, but I do not believe that electricity is the right metaphor for subatomic space. That is intra-atomic space. Instead, the proton is gravity. And that's obviously true. It has not been proved mathematically, although I have. So, whatever words you use, what we want is a consistent language to address quantum space. And again, we're talking about the quantization of energy. Now, energy is the electron, and that's a major clue. The proton is a spatial object. And the reason we can say that, and it makes logical sense, is the proton, when it's in its atomic system, that is surrounded by electrons, you just said it, it's surrounded spherically, which means the proton makes a center in space. That's why it can bend space, which is why that charge, so-called, the plus charge, is not correctly conceived as charge, or not optimally conceived as charge. It's gravity. Anybody can see that, but there are questions that arise after that because this is a paradox. All right, so we have a particle that's at the center of space that it's bending around it. So what is the electron? It is I'll call it an antiparticle. Now you could object to that, especially if you know subatomic particle theory in the standard model version, that there is such a thing as an antiproton and such a thing as an anti-electron, which in the case of the anti-electron is not a proton, is called a positron. However, that is an artificial particle. The positron is said to exist. I question that. It's a mathematical proof that that thing exists, but it's an unnatural sort of a particle. There really, you could say there's either one particle or two, but you cannot say that there are more particles than that unless you go outside the bounds of what is called atomic physics. The neutrino is a perfect example of extra atomic particle physics. And really all 36, however many there are now, last I heard there were 36 of these quasi-particles, and that's what they should be called. They're quasi-particles because they have nothing to do with the atomic system, which is based strictly on just two particles. But the classic particle, as being a spatial particle, is restricted to one of those. So what in the world is the electron? The electron is the manifestation of the waveform of a particle. And an electron is pure wave, to the proportion that the proton is pure non-wave. That's good enough for now. I hope that's not baffling or confusing. It's meant to be simplifying. That the proton is a spatial particle for the obvious reason that it occupies a center of space. And we can say that because the space around it is bent spherically. That is known. There's no question about that. And Einstein actually proved that. He proved it at the gravitational level. But when you have a lot of protons together, such as in the Earth or in the Sun, obviously those protons, as they're bending space, you can integrate that, and that's what gravity is. It's integral protonic centripetal force. And it's very important to recognize the fact, although this has been argued and still is gravity a force? Well, yes it is, because of what I just said. That is what physics knows, is that gravity is nothing more than integral protonic force. So it is a force. It's just it's not at the atomic level, so it has a different characteristic. Okay. So I hope you have a good overview. We're reaching 40 minutes. That's good enough for now. We'll have another lecture today. This is the 8th day of December. I hope you're getting excited, because I am. In fact, I am getting just a little bit emotional, because I've been working on this for 2 years to be able to present this to you in a cogent, accessible, assimilable form. And I'm also writing, as I've mentioned several times, a LaTeX document for submittal to Archive, where I cover this and much more. But I can't let it go on and on and on and on in a scientific document, even to the open source review board. It's really an open source review board for scientists who don't have sponsors, they don't have a professor, they're not PhDs, they have no accreditation. Well, none of these magazines such as Astronomy and Astrophysics wants anything to do with the general public. It's a closed system. That's a problem, but it's actually a human problem, which is hard to get around. So Archive is an incredible resource. As an admiral, I wish I knew more about them. From what I do know, though, they're incredibly reputable and laudatory. In other words, they're somewhat heroic. And just to give you one example in closing, to give you something to think about until the next lecture later today, is Grisha, Grigory Perelman, a Russian Jew who is considered to be the greatest mathematician of all time in his field, who won the Clay Prize, the Millennium Prize, which is given by the Clay Institute for the solution of any one of 7 outstanding problems in mathematics. Grisha solved one of them and was awarded $1 million. He refused it. And then he quit science, he quit mathematics, and he lives in Leningrad, and nobody can talk with him. He will not be interviewed. He's changed his life completely. Some say he's insane. I think he's a hero. He called mathematics corrupt, and he dropped out because he was tired of being treated like a zoo animal, and he would not take the $1 million because it would have compromised his dignity. I find that emotionally elevating. So I very much like Grisha Perelman, even though the problem he solved is meaningless. These guys at this level do not think that problem is meaningless, and if you would like to look into the problem he solved, it's called the Poincaré conjecture. So Grisha, to round out this story about Archive, where I'm going to publish, that's where Grisha published. And it was the article that he published in Archive that got him $1 million. And more than that. He also won another very lucrative prize, which he also turned down. So I hope you enjoy this. We're going to be solving the quantum paradox and the cosmological paradoxes all at once with a new geometry where we penetrate inside the atom, which nobody's ever done to the level that Rudger Bošković and I have done. This is a new form of mechanics that affects universal structure, and it's also a new geometry that affects mathematics and geometry which across the board, and will change our education system completely and totally magnify physics back to its proper level of a positive force for mankind instead of a negative one, which it is right now, exclusively negative. We'll be back. This is Anagalactic with the Secrets of the Universe. Stay tuned and don't forget to keep looking up.